Okay, now look at this first slide, magnetic materials, which you might have studied already in our plus 2 level, and you might have segregated the magnetic materials into different types. But in this unit, we concentrate more on applications of various magnetic fields, especially in engineering and technology. We have already seen in superconductivity that superconductors are good diamagnetic materials, and those materials are having a lot of practical applications like magnetic lav trains, MRI scans, separation of volts, etc. We have seen it. Now, in this unit, we will look into the basics and then the applications and the theories related to magnetic materials. Now, look at the next slide. This is the syllabus of magnetic materials. As we have seen that in the unit 5, we have three materials. One first is on superconductors, next is magnetic materials, the third is on dielectric materials and their engineering and technical applications. In the magnetic materials of this chapter, we majorly concentrate on origin of magnetism, classification of various materials, like dia, para, ferro, antiferro, ferrimagnetic materials, their applications and properties. And some theories, not very rigorous mathematics, but we will see few of them. And then how to design a permanent magnet or how to use a magnetic material for say storage applications like RAMs or hard disks, etc. Now, you have seen all this. You have already used the bar magnets in our lab for various applications. The bar magnets are used for making simple observations like very simple observations like finding the magnetic fields or making another magnetic material to get magnetized. This is a horseshoe magnet, and these are the magnetic needles which we have shown in deflection magnetometers. Cylindrical and oval shaped magnetic magnets which are used for various purposes, and ring magnetic materials which are also used in magnetic levitation demos. This is, you already know all this. Now our aim is to see that why some of the materials are showing magnetism, and thereby what is the origin, why magnetism is arised in the materials, and thereby why some materials are very good magnetic properties and other will not show magnetism at all. And next, see what is the basic relation between various magnetic parameters, and then we will see in this class classification of various magnetic materials based on various phenomena. And look at this first, we look at the origin of magnetism. So we know that any atom, if you take it, every atom will have a nucleus followed by electrons revolving around the nucleus. And we know that the electron is negatively charged and nucleus is positive. So if I take a orbit of a electron is revolving around the nucleus in a fixed orbit of fixed energy given by Bohr's theory. And by quantum mechanics, you also know that the orientation and energy of the orbit is quantized. And also the spin of the electron is also quantized. Now, if I look at this figure, as electron is revolving around the nucleus in a fixed orbit, now I suppose that electron is a point charge. So, in the earlier classes, we have seen that a point charge, if it is at rest, the rest charge produces electric field. A charge is at rest, suppose say, we have seen that it produces electric field. If the same charge E, if I take, is in motion, and a moving charge produces both electric and magnetic fields. So a charge at rest produces E or electric field E bar. A charge which is in motion produces an electric field. A varying electric field is responsible for giving magnetic field B. Therefore, a charge in motion produces this E and B. Now, if the charge is oscillating, E is oscillating charge, if I take it, we say that oscillating charge produces a radiation. And one of the example we have seen is a laser receiver. Now, I can I suppose that an electron which is revolving in an orbit is equivalent to a unit charge moving in a circular orbit. So when an electron moves in a circular orbit, it is equivalent to a simple solenoid. So therefore, a moving charge in a closed orbit produces magnetic field. So therefore, every atom, irrespective of the material you have chosen, must be magnetic in character. So thereby, every material in the universe will have magnetism. But how weak it is, how strong it is, and how these magnetic fields will cancel each other or aid each other, that makes the materials into different classifications. So the first origin of magnetism is orbital motion of electrons. Whereas as long as electron is moving in an orbit, we know that it constitutes a current. And this current that is moving in a closed path will give you a magnetic field. And therefore, the first reason for magnetism is orbital motion of an electron. This orbital motion of an electron will produce a magnetic dipole moment, which is called as orbital magnetic dipole moment. As it is going from here, it is the direction of motion of electron, and it is the direction of motion of electron in this. Therefore, when it is moving in the orbit, I may be getting a north pole here or maybe a south pole, and therefore orbital electron is equivalent to a magnetic dipole. You have seen that a dipole is simply a arrangement of two equal and opposite poles. So I have a north pole here of pole strength M. I have a south pole of pole strength S. So therefore, this is north pole and this is south pole, and this arrangement we call it as dipoles, and thereby an orbital electron will create a orbital magnetic moment. And magnetic moment M, we generally define it as pole strength. This is magnetic moment mu M. I write it as the pole strength is M multiplied by a distance between the two. Maybe suppose say distance between the poles is X or D. So this is the amount of orbital magnetic moment created by an electron. And therefore, the major reason for magnetism shown by a magnet is orbital angular momentum. And the next reason for getting magnetic momentum is okay, because the electron, if I see it, it is not only moving around the nucleus, but it is also moving about itself, which we call the spin of the electron. So the orbital motion of an electron around the nucleus is similar to a current loop. Any current loop will produce magnetism. Therefore, orbital motion creates and gives a origin for magnetism. And a minimum requirement or minimum magnetism that was associated with the moving electron in an orbit is given by E is equal to h pi by m, which I am not deriving here, and this is called Bohr's Magneton. So Bohr's Magneton is the smallest possible value of magnetic moment associated with the electron. If I substitute the charge of the electron, mass of the electron, and the Planck's constant h, I'll get this. Therefore, the magnetic moment associated with a electron is very, very small, but however, there is a magnetism arising out of orbital motion. This is what we simply call it as Bohr Magneton. And the next reason we will see is the spin motion. As the electron is spinning around the nucleus, this is the nucleus, electron if I take it, this is the electron, and in addition to orbiting around the nucleus, it also spins. As the charge is spinning, spin charge will have a spin angular momentum, and that spin angular momentum is responsible for giving magnetic nature to the substance. So every substance also will have atoms orbiting around the nucleus and also spinning about their axis. But you know that when I take an electronic configuration, we have 1s2, suppose say first orbit, and I'll take 2s2, and then I'll take 2p2. In this case, these two are completely filled. But we know that if I take any one of these orbit S, I can put two electrons, one up and one down spins. Therefore, the electron spin is having only two values, plus half or minus half. If in an orbit, if I take any of the orbit, just like for example, this is an orbit. Okay, this is the nucleus. And in the orbit, if I select one electron, it will have up spin. So that means it is completely filled. If I choose the next electron also that is moving in the same orbit, it will have spin down. Therefore, the spin magnetic moment arising due to the first electron is compensating the spin magnetic moment due to the second electron because their spins are opposite. Therefore, the two spin magnetic moments will cancel each other, and a net magnetization due to these field or electrons in the orbit is zero. That means whenever you have an orbit which is having electrons with opposite spins and completely filled, then we don't get any contribution of magnetism from the spin of the electrons. But instead of this, if I take it, I now consider 2p1 or maybe 2p3, something like this. If I take it now, the outermost orbit will have only one electron. If there is only one electron, this will have either up spin or may have down spin. Or I can take the down spin, something like this. So thereby the net spin moment will not be cancelled and it will be added. This is the example for only one atom. But we know that there are a lot of atoms in a given material. As there are a lot of atoms are there, all those spins which are not compensated, okay, will add up and the magnetism due to spin will increase. Therefore, we say that the second most important contribution to the magnetism in the materials is due to the spin motion of electron, which gives you spin magnetic moment, and the spin magnetic moment will have a smallest value given by Gs into E by 2m into S, where S is the spin and Gs is called spectroscopic splitting factor or Landis G factor, and this G factor depends on various parameters on how the magnetic moment, orbital magnetic moment and spin magnetic moment are coupling each other to give magnetism. So even though spin motion is giving rise to magnetism, because of the parallel spins or opposite spins, they cancel each other, and only some materials, which materials? The materials which are having uncompensated or unpaid electrons are capable of giving the magnetism. Therefore, transition metal elements whose d orbitals are not completely occupied or rare earth elements. So the transition metal elements you can take copper, etc. And rare earth elements you can take niobium, okay, or you can take something like europium, or you can take some other say ND, etc. So these rare earth elements are having unpaired electrons, and thereby their p orbital is not fully occupied. Therefore, the spin magnetic moments are not cancelled by each other, and they have net effect to spin magnetic moment. And this spin magnetic moment is responsible for giving magnetism. But however, most of the materials will have magnetism, almost all will have magnetism, but some of the magnetic effects due to the interaction, they will be dominant, and some other are not such a dominant magnetisms. Therefore, the weak magnetisms like diamagnetism is suppressed by strong magnetisms like ferromagnetism. And the third reason, the first is okay, origin of magnetism. Third reason, if I take it, before going to third reason, I am now summarizing the combination of orbital momentum L and the spin momentum S of the electron S. Okay, how they are coupling? There are a lot of coupling schemes. How L and S interact and couple together to give total magnetic momentum J, and this coupling depends and can be calculated by using various methods, and they are called LS coupling. How L and S are coupling, this is the one method, but all these are not there in the syllabus to discuss, but you can refer any textbook to know what is LS coupling. And we have RS coupling also is there. So these coupling schemes will explain how to uh, get the total magnetic moment J, and depending on the J we can see what is the net effect of the magnetism. If we take an atom, if the shell is half filled, then the total magnetic moment is L plus S. If the shell is less than half filled, then the rule is J is equal to L minus S. I'm talking about the total magnetic moment L and the total spin moment S. And the shell is half filled, J is equal to S. If some shell is completely filled, because the upspin and downspin and orbital momentums are cancelled together, therefore I'll get 0 S. And such materials will not show the dominant magnetisms. These are the schemes. So instead of in addition to this, we have the third origin of magnetism, and that is nuclear magnetism. Why nuclear magnetic moments are there? We know that within the nucleus, this is the orbit, electron orbits. If I say this is the nucleus, you know nucleus contains both protons and neutrons, and these protons and neutrons, they are also spinning, both of them will spin, and because of these spins there is a net magnetic moment, and the total magnetic moment due to all the protons that are in the nucleus will give rise to nuclear magnetic moment. But however, the mass of nucleons is much higher when compared to electron. Therefore, we know that if m is the mass of a proton, which is equal to almost 1832 times the mass of electron. Therefore, electron mass is less, hence magnetic moments given by electrons due to orbital motion and spin motion is much more compared to this. Since we have seen that magnetic moment, if you take, it is Eh by mu, if I take it 4 pi by m. As m increases, then mu decreases and magnetic field contribution decreases. Hence, in most of the cases, the nuclear magnetic moment is to be taken as very, very small, and it will be neglected. And but it is also an origin of the magnetism in materials. In some cases, the nuclear magnetic moment of nucleus may be in external magnetic field is coupled with the J, that is the total magnetic moment of electrons. Therefore, the net effects are different. But however, if I summarize it, there are three reasons for getting magnetism in magnetic materials. The first reason is orbital motion. So orbital motion is equivalent to a current loop. A current loop will give you a magnetic moment. So orbital motion of electrons, if I take it, this is the first reason. And the second reason for the magnetism is spin motion. Electrons will spin about themselves while moving in the fixed orbit around the nucleus. So spin motion of an electron also gives and responsible for magnetism in a given material. Third one is nuclear, and this is very small, and it in most of the cases it will be negligibly small. These are the reasons. Okay, now if you have any doubts on this, you can ask your questions by typing in the chat box. So now we will see the next one, some basic relations. And these basic relations you have already learned in the earlier classes. But I'm just to recapitulate, I'm just writing down all those expressions. We already know that when a charge E or Q is placed in an magnetic field which is moving with a velocity v, a force called Lorentz force acts on it. That force is given by F is equal to the charge Q into V cross B, or it's a cross product, and this is the force that is acting on it. But we are also seen that the force that is acting on the charged particle due to an applied electric field E is EV. So if I have a charge in electromagnetic field, the total force F will be the Fm plus Fe. So I'll get this as a total force acted on this. And this force is important when a charged particle is moving in an electromagnetic field or an electric field or in a magnetic field, and thereby the path of the one you can see it. So now the magnetic field strength H. Don't confuse between BH. B is magnetic induction or magnetic fields. H is magnetizing field. That is external field you are applying to magnetize or demagnetize a material. So the magnetic field H is generally measured in terms of ampere per meter. B will be either in terms of Tesla, or if I go for CGS unit, I may use instead of Tesla Gauss. And those who have done some experiment like say BH curve, or those who did the Hall effect, they might have already measured these Gauss and Tesla while measuring the magnetic field created by electromagnet. And you can also do the measurements in our physics lab. So this is the magnetization or magnetizing force or external magnetic field applied is H. And we know that whenever you have a magnetic field H, there will be number of magnetic lines that are going in the direction. How many number of magnetic lines of forces are going, and how many are there per unit area, we call it as magnetic flux. So how many number of magnetic lines of force are there per unit area, we call it as magnetic flux. Why? And this magnetic flux when you are calculating, we calculate the number of lines perpendicular to the magnetic field B. So, but when I place a magnetic material in an external magnetic field, suppose say this is the external, some other material I am keeping in the external magnetic field. So this is the H. Okay. So how quickly, how easy or how difficult for this material to get magnetized is called magnetization. So this magnetization, when I consider it, it is called as M. So some books, they also write it as intensity of magnetization I. So we can use as I or M. So the process in which the materials are get magnetized. But the process when you are magnetizing, that depends on the capability of the materials that allow magnetic lines of forces through it. That means if I take a material something like this, any material, maybe magnetic material, then some of them easily allow the electric magnetic lines of forces into it. But if I take some other materials, what happens is they don't allow these material, the magnetic lines of forces into it, they repel. That's what diamagnetism is. They repel each other or only one will. If I take some other material, most these material, some other materials, they take more of them into it. Many lines will go into it. So the property of the material that allows the magnetic lines of forces that go into it, okay, is called permeability mu. Mu is the permeability. And mu naught is the permeability of free space. And if I take mu and mu r relative permeabilities, so the ease with which the magnetic lines of forces are moving into the material, okay, is described by permeability of the material. If the permeability is good, most of the lines will go into it. It is something like a resistance for a conducting material. So the ease with which the magnetic lines are moving within the magnetic material is called permeability. And that permeability mu naught, applied field H, magnetization M are related to magnetic field B, as B equal to mu naught into H plus M in free space. Okay, and the free space magnetic permeability is given by this value. It is a constant 4 pi e to the power minus 7 Henry per meter. And the ratio of M by H, magnetization by magnetic field strength, is called chi, the magnetic susceptibility, which we have seen this in superconductor. In superconducting material, we have seen that it is -1, therefore superconductor is a superconductor is a material that has diamagnetic properties with perfect diamagnetism. Now we will see how the magnetic materials are classified into various types and based on which the magnetic materials are classified. So the classification of magnetic materials is based on various methods. One, depending on the magnetic susceptibility. Is the magnetic susceptibility is small or large or negative or positive, small and negative, small and large, negative and large, something like that. If I take like depending on the magnetic susceptibility of a given material, the magnetic materials can be classified into various types. And how the magnetic susceptibility changes with the temperature T, also you can classify them into categories. materials. Not only that, what is the behavior of a magnetic material in an external field? That means if I take a material like this, how it is behaving when an external field is applied. Is it attracting? Is it opposing? Depending on that, the materials can also be classified into various types. And based on another one, as we have seen that there are uh, electrons which are revolving around the nucleus and giving you the dipoles. And these dipoles, spin dipoles or maybe orbital dipoles, or the combination of this, we have dipole movement. And how these dipoles are arranged in a material, depending on this also you can segregate the materials. So magnetic dipoles. So magnetic dipoles are nothing but uh, one negative north pole and we have a south pole, and they are get separated, and north pole south pole separated. This is a dipole, simple dipole, magnetic dipole. How these dipoles are there within the material is important. Do material will have dipoles, or is it that the dipoles are randomly arranged, or they are arranged uniformly within the material by themselves or by external field is important. So based on this various methods, the magnetic materials can be classified based on magnetic susceptibility, the behavior of the magnetic material in the external magnetic field, and how the orbital or say spin or say total dipole moment is oriented in a given material. Thereby, the materials are classified into several categories like diamagnetic materials, paramagnetic materials, ferromagnetic, ferrimagnetic, and antiferromagnetic materials. And in this unit, our emphasis is on last three: ferromagnetic, ferrimagnetic, and antiferromagnetic materials. Since at plus two level, you studied lot about diamagnetic and paramagnetic materials. Now we will concentrate more on the last three, especially ferro, ferri, and antiferromagnetic materials, to see the engineering applications of those materials. But however, I will define what is a diamagnetic material, how it behaves in external field, similarly for paramagnetic materials also. So can you type in the chat box what are the applications of these magnetic materials? Any one of these five different classes. So you just try to type your answers, the uses of magnetic materials in various fields. Yeah, yeah, 34. Pranit is a compass navigation. Okay. Now in navigation field, instead of using the compasses, we are using gyroscopes. And we have optical gyroscopes, laser gyroscopes, especially they are used in uh, planes, aeroplanes, and ships, because they are very superior in deciding the direction in which the given aeroplane is moving. Yeah, Krishna Chaitanya preparing hard disk. Yes, HDDs. Hard disk drives contains the sprinkled microcontrollers of ferromagnetic materials like iron or cobalt or mixture of that. So magnetic materials are used in making hard drive disks. Any more applications you can see? Yeah, any other applications anybody can type? some of other important applications of magnetic materials. So magnets are high power magnets are used for various applications like MRI scan, what we have seen in the superconductors. Yeah, in speakers, correct. We have magnets in speakers. So let's try to find out some more applications by yourself, but we'll continue our class to see each of these five different types of magnetic materials. So the next slide is, and if you want to find more detailed explanation of these magnetic materials, please visit this website, all of you. And this website gives you more details about some of these magnetic materials. Now see that I have now segregated the magnetic materials into dia, para, ferro, antiferro, and ferrimagnetic materials. But diamagnetic materials, the first important property, if you see in the slide, is that they get weakly magnetized. So magnetism is a weak magnetic property. It's a weak magnetism. That's why even though all materials will have orbiting and rotating electrons, they don't show this magnetism because it's a very, very weak one. Next is that the strong magnetism, ferromagnetism, antiferromagnetism will shield this weak diamagnetic properties also. So that means every material that is there in the universe is a diamagnetic material. But the diamagnetism shown by the material is very, very small, which we cannot recognize. Therefore, the diamagnetic materials are those which get magnetized weakly in the opposite direction of external field H. If you have like they get magnetized, if this is the H direction, then these magnetic materials get magnetized in the opposite direction, but weak, very weak. And there are no magnetic dipoles. This is the most important, that diamagnetic materials have no dipoles at all. Okay, so dipoles are also called as spins, but don't confuse the spins with the spin of the electron. The spins means that how the total angular magnetic moment J is aligned, and this J we generally in magnetism called as spin. How the total magnitude of the say magnetic moment is aligned within the substance is important. Therefore, there will be, we say, no spins at all in diamagnetic materials. And don't confuse the word spins here I am using for the spin of the electron. This spin is the spin of the spin of magnetic moment, how the magnetic moment is aligned with respect to applied field. Here there are no magnetic dipoles at all. And paramagnetic materials, when they are placed in external magnetic field, they get magnetized very weakly or feebly in the same direction of applied field. That means if H is in this direction, they also get magnetized in the same direction, which is opposite to diamagnetic materials. But these paramagnetic materials possess permanent magnetic dipoles. So suppose say this is the direction of a small magnetic dipole, and this is another direction of magnetic dipole, and these are, suppose if all of them are aligned in the same direction, net effect is very large. But in paramagnetic materials, the spins or say the dipoles, magnetic dipoles are randomly oriented. Means that one of the dipole, if it is in the direction like a parallel direction, something like this, the next immediate atom will show, or the another atom will show a magnetic dipole moment maybe in this direction. and other will show a magnetic moment in this direction. Some may show like this, some may show like this, some may go like this. That means all the magnetic dipoles are randomly distributed so that they cancel each other and net magnetization is zero. Right? Even though paramagnetic substance is possessing dipoles, all of them are randomly distributed. Therefore, there is no net magnetization of paramagnetic materials. But this is true when there is no external field applied to the material. If I apply external field H in this direction, then all of these magnetic dipoles try to orient in the direction of applied field. So all of them go. That's why we say they get magnetized in the direction of applied field. But there are no such dipoles in diamagnetic materials. So therefore, once when H is not there, they are randomly distributed. When H is there, they are aligned or they are oriented by the force F, because we have seen that an external field H gives a force F on the dipoles, and dipoles orient themselves in the direction of applied. So this is the spins alignment in paramagnetic materials. Whereas if I go for the next magnetic materials, that is ferromagnetic materials, these ferromagnetic materials get strongly magnetized, okay, in the direction of external magnetic. That means if H is like this in this direction, the applied field is in this direction, and once the ferromagnetic material is placed in the external field, they also get magnetized. So thereby you can see the randomization of magnetic dipoles, and you can see the ferromagnetic alignment of dipoles. So in a ferromagnetic material, dipoles are present. Here, no dipoles. Here, dipoles are there, but randomly arranged. Therefore, net is zero. Random arrangement gives you net magnetization. In ferromagnetic materials, they possess the magnetic dipoles. These are called spins, and they all of them are in the same direction. Even H is zero, no external field is applied, still they show the alignment of magnetic dipoles in the same direction. When they are showing in the same direction means that net magnetization is not zero. That means even in the absence of external magnetic field, they show magnetism. Hence, such a property of showing external, such a property of showing magnetism without applied external field is called spontaneous magnetization. So, spontaneous magnetization is a process of showing net magnetic dipole moment even in the absence of applied field. So, that is the most important and fundamental property of ferromagnetic materials. Ferromagnetic materials will have aligned magnetic dipoles in the same direction. But look at this. They are not only arranged in the same direction, but their magnitude is also same. Therefore, ferromagnetic materials will have dipoles of equal magnitude and also aligned in the same direction. Therefore, net magnetization is not zero. Now, if you go for the next class of magnetic materials, which we call anti-ferromagnetic materials. Look at this ferromagnetic. That means these also are also ferromagnetic, but it is anti-ferromagnetic spins will be there. Therefore, it is a subclass of ferromagnetism. Hence, if you place these anti-ferromagnetic materials in the external magnetic field, they get strongly magnetized in the direction of applied field. Again, in this direction of applied field, they get strongly magnetized. They do possess spins like this. Magnetic spins are possessed. But most important thing is that these spins will cancel each other because their magnitude is same, but direction is opposite. One is up spin, the other is down spin. Therefore, if I have spin up and spin down like this, if you apply an external field H in this direction, all of them try to move in the same direction. Therefore, they are strongly get magnetized. The spin arrangement is most important to segregate the ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials because they are having parallel or anti-parallel spins of equal or unequal magnitudes which are oriented in the same direction or in some directions. But however, in diamagnetic materials there are no spins, but in paramagnetic materials spins are there, but they are randomly distributed, therefore net magnetization is zero. So coming to the next type of magnetic materials which are called ferrimagnetic materials, they also get strongly attracted in the direction of external magnetic field. They do possess permanent magnetic dipoles, but they are unequal and anti-parallel. So this is larger and this is small. This is large and this is small. Therefore, net magnetization is not zero. So the net magnetization in this case is zero, but in this case net magnetization is not zero. So therefore, a ferrimagnetic material is one which possesses magnetic moments in opposite directions with unequal magnitudes. So these unequal magnitudes makes a net magnetization non-zero. And the other classifications of these materials are, I have given some examples here. So one of the example is for diamagnetic material, very known precious metals like gold, silver, etc. And the examples of paramagnetic materials are oxygen, copper, Cu2 plus, copper chloride or Cu2 plus ion only, but not copper. And ferromagnetic, there are many: iron, nickel, cobalt, all these are ferromagnetic substances. And antiferromagnetic materials, manganese oxide, manganese sulfide, etc., are antiferromagnetic. And ferrimagnetic materials, which are generally used in antennas, they are called ferrites. We have zinc ferrite, nickel ferrite, and many other ferrites are there. We will discuss them while discussing ferrimagnetic materials. And next important segregation is depending on the magnetic susceptibility chi. For all diamagnetic substances, it is negative and small. Negative and equal to 1 is perfect diamagnetism, which is a superconductor. Paramagnetism, if you take it, it is small and a positive. And magnetic susceptibility, as we have seen that magnetic susceptibility chi m is a ratio of magnetization m by h. So if I take m by h ratio, this is negative and small. This is positive and small. This is positive and large. This is small and positive. This is very large and positive. Thereby, you can classify the materials into various categories. But the magnetic susceptibility chi is function of temperature. So how it varies is also important. For diamagnetic materials, it is not temperature dependent, it is temperature independent. Here, in paramagnetic substance, it is inversely proportional to temperature, and C is called a constant called Curie constant, but still it is temperature dependent. In ferromagnetic materials, the materials will be something like chi is equal to C by T minus Tc. Tc is called Curie temperature. That means ferromagnetic materials show ferromagnetism from certain temperature to Tc only. If you increase the temperature beyond Tc, which is called Curie temperature, they are no more ferromagnetic materials. So ferromagnetic materials, if you take them and if you keep these ferromagnetic materials above Tc or Curie temperature, they will convert into paramagnetic substances. So ferromagnetic materials will become paramagnetic materials at temperature greater than Tc. That's why chi is a temperature dependent one. So when if you see this chi, why it is increasing temperature more than Tc is converting the ferromagnetic materials into paramagnetic materials. We have seen that the ferromagnetic materials will have spins exactly equal, okay, and oriented in the same direction, something like this. Now, as if I increase the temperature, increased temperature increases the kinetic energy or thermal energy in the substance. As T is increased, the chaotic motion or the motion of the dipole moments also increases. As they get more energy, this dipole starts vibrating, and at a temperature greater than Tc, they will be oriented randomly by losing their alignment. So this is the alignment at a T less than Tc. As T is greater than Tc, they will get randomized. Once they get randomized, then this is the property of a ferromagnetic material. Therefore, a ferromagnetic material up to Tc, it shows ferromagnetism. Above Tc, it will be a paramagnetic material. When coming to antiferromagnetic materials, the chi-m, which is magnetic susceptibility, is also temperature dependent, but it varies T plus Tn, where Tn is called Néel temperature. Below Néel temperature, it shows antiferromagnetism, and above Tn, it becomes paramagnetic material, since the oppositely arranged spins in this magnetic material at a temperature greater than T greater than Tn, they get again randomized. So one will go like this, other will go like this, randomized. Because of randomization, they lose their antiferromagnetism and they become paramagnetic. And coming to ferrimagnetic materials, okay, this is also temperature dependent, but it is plus or minus Tn. And again, there is a Néel temperature, and this Néel temperature may be different for different materials, and is also different from anti-ferromagnetic materials. And up to Tn, they are ferrimagnetic materials called ferrites, and after that, they are paramagnetic materials. These are the classification of various materials based on the condition of external magnetic applied magnetic field, the magnetic susceptibility and behavior of magnetic materials in external field, and the temperature dependence of magnetic susceptibility. So this is the general variation of chi with temperature K. So paramagnetic materials, as the temperature decreases, K goes, okay, which is very low, but chi value is very low here with the temperature. If you take it at low temperatures, as the temperature increases, chi goes on like this with a property as C by T. Whereas in case of ferromagnetic materials, there is a Curie point, and this Curie point we call it as Tc. Okay, up to Tc, they are ferromagnetic materials with large chi. Chi value is large. But after Tc, they are similar to paramagnetic materials, and it is C by T minus Tc is the relation the ferromagnetic materials follow. If I take antiferromagnetic materials, this is called Tn, that is as simply as Néel temperature. Below Néel temperature, they are showing antiferromagnetic behavior, but above Tn, if I go above Tn, they are just like paramagnetic materials. They follow the relation of T minus T. These are the various uh, graphs that are showing variation of magnetic susceptibility with temperature. I stop the class here. If you have any doubts, you please ask me and we'll try to clarify those doubts in the chat box. So you just type it, your doubts will clarify. Or you can ask me also. Those who are there, you can ask the doubts. So if you ask the doubts, we'll try to clarify it and I close this. Any particular one? Okay.